Good morning, class. Welcome to science. Today is Monday, May 18th, and let's get started. So we're starting a new unit on energy, and this is going to be our last science unit of the year. I do want to encourage you, if you want to, you can continue doing any of the activities in the rest of your Ultimate Science notebook. Reach out to me if you want further kind of directions and things like that. I've also been posting it on my Google Classroom. So just know that it's important over the summer to keep reading, to keep practicing, and to keep our mind engaged, even if it's only for 10 to 20 minutes to 30 minutes a day. So we're going to start by taking some energy notes. This is what it looks like. So this should actually be the next clean page in your Ultimate Science notebook because this is after the last unit we did on matter and change. And then we jump back to do oceans. And so now we're back right after matter and change. Looks just like this. So, and remember in my notes, anytime that there are all capital letters, except for in this case where it says energy notes, that's a place where you need to fill in the blanks. So energy is the ability to do work or bring about a change. And when we think of work, we think of like what I'm showing in these pictures here. People, in meetings, on laptops, doing whatever. What this kind of work means is just bringing about any kind of change. So believe it or not, I know I'm working by teaching you right now. Just by waving this marker in the air, I'm doing work, right? The marker was here, I'm moving it here. The marker was here, I'm moving it here. That's bringing about a change. This is work. So work is really just using any energy to do anything. There are only two things in the universe, and this is mind-blowing to me. So think about it. There are only two things in the universe, matter and energy. So just think about that. In all of existence, ever, the only two things that have ever existed are energy and matter. And I know now we're discovering more about antimatter and dark matter and dark energy and things like that, but it can be basically simplified down to these two substances that make up everything that's ever existed. And to me, that's one of the coolest things ever. And it's something that we are going to use in every other facet of science for the rest of our lives. A force is the power or strength used to make that change. So, like I said before, I'm doing work, right? The marker is moving. I'm bringing about a change. This is work. I'm using the energy from my arm to move this marker. If I move it very slowly, I'm doing very little amount of work. If I'm moving it really fast back and forth, I'm using a greater force and I'm using a lot more work. The law of conservation of energy states, remember the law of conservation of mass? Energy is not created or destroyed. It only changes form. So energy can be put into two major categories, potential and kinetic. So remember to fill potential and kinetic in, and I'm going to talk about what those two things are in just a second. Actually went back away too soon. Potential energy is the energy an object has because of its position, condition, or chemical composition. Potential energy is the kind of energy, because energy cannot be created or destroyed, it's the kind of energy we don't really think of as energy. It's the energy before something happens, right? So when I'm holding this pen up in the air, a lot of you might think it doesn't have any energy. It's not moving, it's not doing anything right now, it's just chilling. If I let go of it, however, it's going to move. So the energy that it's moving right now wasn't just created out of thin air, right? The energy didn't just shoot up into the marker at the last second. The energy came from gravity, from its position. So it has potential energy in its location, the ability to move, but it's not until I let go that it actually does. So that's what potential energy is. The energy an object has because of its position, condition, or chemical composition. I want to give another example, and I'm in my kitchen. I'm going to use, let's use some chocolate. So if I ate this chocolate right here, it has 10 calories per serving, so 1 teaspoon. So if I ate a teaspoon of this, I would then get energy, right, stored in the fat cells of my body. It didn't just magically get created that I can now move my arms and things like that. I had to eat something first. I can't just create that energy myself. And so the energy came from something like this chocolate, right? So I ate it, the energy is stored in this chocolate, and then it's transferred to me. So this is another example of potential energy. You'll get a lot more of this in 6th grade. It's just kind of a good setup. Gravity is the force of attraction between objects due to their masses. Basically, it's a smaller object being pulled on a bigger object. And we usually use this to mean the force pulling something down. So when I drop this marker, we all know that it's going to fall, right? Because gravity is pulling it down. My marker is the small object. The earth below me is the big object. They're attracted to each other. The marker will fall down. Kinetic energy is the energy an object has due to its motion. So anytime it's more of the active energy. So anytime an object is moving, it has kinetic energy. And it's shifting back and forth constantly between these two types. So I want to kind of give you the demonstration that I would usually give in class. So our little chanty thing for this is potential. We squat our feet down and we're building up all this potential energy in our legs. You should be able to feel like kind of a burn in your legs. And that's because of all that potential energy building up because of our position. And then kinetic, whoosh, we let it go, right? So potential, kinetic, jump. That's my fun. Kinetic, potential, that's the difference. So when we're squatting down, that's potential. When we're jumping, that's kinetic. Okay, so now we're going to do a simple experiment called the Potential Kinetic Energy Rubber Band Lab. So the question we're asking ourselves is, how far you pull a rubber band back affect how far it's able to travel? So we're going to take a rubber band. And again, this is a very easy one to do at home. So feel free to go outside, grab a ruler, grab a measuring tape, ask your mom or dad if they have any building supplies, because those tape measures are really awesome to use for this. Highly recommend you go try this experiment, but of course you're not required to. You can use a hair tie, you can use a traditional rubber band, you can use a vegetable rubber band. Any rubber band will work for this experiment as long as it's the same type of rubber band for every trial. Oh, I'm out of breath from all that jumping. So write your hypothesis. Remember, our hypothesis is an educated guess. And then fill in the parts of our experiment. So what type of data are we collecting here? Quantitative with numbers or qualitative with words? I'm going to share in 3, 2, 1. This is quantitative because we have numbers. We're measuring how far it goes. Independent variable, what do we want to test? I'm going to give this answer in 3, 2, 1. This is how far we're pulling the rubber band back. So the only thing we're changing is how far we're stretching that rubber band. The dependent variable, how will we measure it? We're going to measure how far our rubber band then travels, right? And then finally, what do we need to keep the same for the experiment to be fair? The same person should be shooting a rubber band each time. You should use the same type of rubber band. The rubber bands should be about the same oldness. They should be the same temperature, even though that doesn't matter quite as much here. And those are all really good things. So all we're going to do is distance stretched back, distance traveled. That's our experiment. So I'm going to start by seeing how far my hair tie will stretch. So my hair tie will stretch 19 centimeters. So I want to make sure that I'm building up to that distance. So I am going to label mine, and you can do yours however makes most sense for your rubber band. For me and my rubber band today, I'm going to do 0 centimeters. I'm going to do, and that's kind of just as my control group. Then kind of regular slack is 7. So I'm going to do maybe 8. So I'm going to go 0, 8, 10, 12, 14, 16, 17, 18, 19. Kind of pulling it back further and further. Okay, so test 1, I'm at 0, and I'm just going to kind of let it go. 3, 2, 1. And so my rubber band, if you're keeping it back with me, on my left side of my chart, I stretched it back 0 centimeters. The distance it traveled was actually, and this is where negative numbers come in handy because it's actually backwards of where I was lining up my rubber band with the floor, by 5 centimeters. So it would be a negative 5 centimeters that it traveled. Really cool when we get to use negative numbers in math. So now I am going to stretch it back. I said 8 centimeters. Some students like to use the edge of the ruler just to make sure it's actually super accurate in the distance that we're pulling it back. So you ready? 3, 2, 1. All right, so now I'm going to measure this and come back to you in a second. Okay, so even with that short distance pulled back, so we had distance stretched back was 8 centimeters, distance traveled was actually 72. So I'm going to create my own chart on my whiteboard just so that we can double check that we're doing this correctly. So for the first one, 0 centimeters pulled back. The distance was, I think I said -5 centimeters. Second time we pulled back 8 centimeters. The distance traveled was 72 centimeters. Okay, so now let's continue. And my dog is just psychotic today. Puppy, shut up. It's just the lawnmower. All right, so I'm lining this up. Last time I did 8. This time I'm going to do 10. So slightly stretching it back a little bit more, and it can be a little tricky. 3, 2, 1, go. All right, so I'm going to pause and come back to you with my measurement in a few seconds. Awesome. So my next line, I'm going to write, I pulled it back 10 centimeters. Always important to include that unit. And it went back, believe it or not, 263 centimeters. So pretty far. A constant that I didn't mention before that I am keeping as I'm doing this is I'm only measuring it up to the front part of the rubber band on the floor. If I measure it at different spots each time, that would not give me a fair experiment. So now I'm going to pull it back 12 centimeters. And let's see what happens. Pulling it back. 3, 2, 1. Super far. I'm going to pause and I will get back to you in 1 second. All right, so my 12 centimeters, believe it or not, went really far. 12 centimeters was 480 centimeters. 480 centimeters. So it's really picking up quickly. Let's move on to our 14 centimeter measurement. So I have my ruler. I'm going to shoot it off in a different direction. So it has to give myself a little bit more space because I'm worried it's going to hit the wall. My apartment isn't super huge, so we're doing the best we can with the limited environment. So I'm going to shoot it this way this time. 3, I'm at 14 centimeters. 3, 2, 1. All right, I'm going to measure and get back to you in 1 second. Awesome, so 14 centimeters actually went 500 centimeters long. So actually not that much further than our 12 centimeters. Let's do now, so we're filling this in our chart. We've done 1, 2, 3, 4, 5. So you should have 1, 2, 3, 4, 5 lines filled in. 2 more to go. Now I'm going to pull it back 16 centimeters. So let's see how this goes. Go in the other direction. My hair looks awesome after dragging a ruler, all across the floor. Wonderful. Pulling it back to 16. Whoops. Try not to hit yourself with it. That is kind of painful sometimes. 3, 2, 1, go. All right, that also went pretty far. I'm gonna get back to you in a few seconds with that measurement. So this one actually went 558 centimeters when we pulled it back 16. So now on our chart, you should have all of them filled in except for the last one. If you're following along with me. If you're doing this outside with your own rubber band, congratulations, do the best that you can. Try not to hit any person or animal in the process. So now I'm pulling it back to 19 centimeters, feeling like it's gonna hit the wall over here, but we'll see. 3, 2, 1. It did. But we're gonna do the best that we can to measure it. I'll be back in 1 second. So our last one did hit the wall, so it's not quite accurate, but 19 centimeters pulled back went about 700 centimeters far. Okay. So now, going to the next part of our experiment, you need to say, my hypothesis was correct and verified, or incorrect and falsified because, and explain how the data supports this. How does this experiment show a relationship between potential and kinetic energy? The experiment shows a relationship between potential and kinetic energy because, and this right here is the most important part of the experiment, the more I pull it back, the more I'm increasing the potential energy, right? This might not look like it has energy, but it's building up tons of that potential energy here. As soon as I let go, that's when it becomes kinetic. So it's going from potential, kinetic, right? Potential, kinetic. What other experiments might show the relationship between potential and kinetic energy as this one does? So an example might be, does squatting down further make me jump higher? Does bouncing more times on a diving board increase the size of the cannonball? Something like that. Then you need to graphic The type of graph you should use should be a bar graph because we're doing separate variables. And then our final activity for today, sort the pictures of potential and kinetic energy. Feel free to pause on any of these, and this is our answer key. So the energy in food should be